Before we begin, it's necessary to make sure that we know how to differentiate generic functions that look like this, just written as f of x. If I give you something like this, assuming f is a function of x, we would symbolize the derivative as just f prime of x. So what would you do with this one here? You would recognize it as a chain rule problem. The outer function is the fourth power, and the inner function is just the generic function f. So you'd work the chain rule on it, and you'd say 4 f of x cubed, and you can put that in brackets, multiplied by, now by the chain rule you would just say times f prime of x, and leave it at that. Now notice, this is an easy thing to do. This is an easier problem than had I said, say, sine to the fourth of x. To differentiate this, right, you could say, okay, the derivative of the outer function is still the fourth, so you'd say 4 sine cubed of x. But you have to know what the derivative of sine x is to complete this. You need to know that it's cosine x. If it's written this way, this is actually an easier problem because you don't need to know what the derivative of f is. You just have to symbolize it as f prime. So keep that in mind. A couple more examples. Here's another chain rule, only this time the outer function is f and the inner function is x cubed. So working the chain rule on it, it would be the derivative of the outside, which is f prime of x cubed, keep the inside, multiplied by 3x squared. That's it. And lastly, you can have these in combination with product and quotient rules. So this one would be a product rule. So that's, call that f, call that g. And so if we worked it out, that's f prime g. So that's 2x f of x plus g prime f. So that'll be x squared f prime of x. You know, we're gonna need to understand how these problems work if we're going to proceed with the implicit differentiation lecture. All right, so take this one. X squared plus y squared is 25. At first, if I want dy dx, your instinct would probably be to isolate y and then just differentiate as normal, because up until this point y was always isolated. So let's do it that way. If we isolate y, you bring over the x squared and take the square root, and you get, I'll do it up here, you get y equals plus or minus the square root of 25 minus x squared. Then we can differentiate this as per the usual rules. Right, you just do d dx on both sides, so d dx. I mess with the notation, I put the parentheses around the entire thing to indicate that I want to do the same operation to both sides. So that would be, we get dy dx on this side equals, by the chain rule, you'll get plus minus 1 over 2 square roots of 25 minus x squared. And then by the chain rule multiplied by the derivative of the inside, which is minus 2x. And if you simplify that, move this over, if you simplify that, what you get, I'll put it in the corner here, you get dy dx equals plus or minus x divided by the square root, the 2's cancel, 25 minus x squared, right? This minus and this plus and minus is basically a wash. It's going to be plus minus either way. This is what you get. Now, that's called explicit differentiation. If we want slopes of lines tangent to this curve, which by the way is a circle centered at the origin of radius 5, if we want slopes of tangent lines as a function of x, all we got to do is plug in various values of x. And that's going to give us the slopes. There's a couple problems here with this plus minus. I mean, how do you know which one to use? That's going to depend on a little bit of common sense just by plugging it in. If you want the slope at, say, x is 3, you make x 3, plug it in, and if you want this one, you have to know to take the minus sign because it's going to be a negative slope, and if you wanted the one down here, you would have to know to take the positive slope. There's a different way of differentiating this without isolating y, and that's called implicit differentiation. What we're going to do is leave this just as is and do the differential operator to both sides just as is. So let me get this out of the way. So I'll do d dx. Again, I abuse the notation by writing the parentheses around both things. So I'm going to differentiate both sides of this. I'm going to go through it real slow though. The derivative with respect of this side is the derivative with respect to x of both individual pieces. So this equals d dx of x squared plus d dx of y squared equals, the derivative with respect to x of 25 is just 0. I don't have the room here, so I'm just going to write 0. Alright, 25 is just a constant. Now, this d dx of x squared, we know what that is. That's just 2x. Question is, what do we do with this? And the way that you have to approach this is you have to recognize this, you have to treat y as though it is a function of x. See it like it's, instead of a y there, we have y equals f of x. You should see it that way, just written in a slightly different form. So it's going to turn into a problem that's like one of these, right? It's actually very close to this thing here. We need the chain rule for this. There are two functions going on here. The outer function is the squaring function, if you can see that, right? That's a y squared. The inner function is the unspecified function y. We're treating y as though it is a function of x. So there are two things going on here. We have to differentiate both of them. So the derivative, we need chain rule for it. So the derivative of the outer function is the squaring function. That's going to be 2y. Right? That takes care of the squaring operation. But we have to multiply that by the derivative of the inside, which we're going to write either y prime, just like we wrote f prime for the other ones, or it might be more explanatory if we write it as dy dx, just to emphasize that y is a function of x equals 0. So that's how to take care of this, and that's what this video is about. Now, I want to isolate dy dx, so pull this over to the other side, and then divide by 2y, and you get dy dx ultimately is minus x over y after the 2's cancel. So you look at this and compare it to the answer that we got when we did it explicitly. What we got was, we got dy dx was minus x over y. Now they don't look like they're the same, but they really are, because if you remember, this thing here is y. If you took y from the original expression and you isolated it, this is what you got. So when you do it implicitly, it shows up this way. Now there are certain advantages in this, because if we come back to the circle, if you want to know dy dx at a specific point, say since this is x squared plus y squared is 25, the radius is 5. If I go like say here, this is 5, and I got a 3, 4, 5 triangle here. This would be 3 and 4. Right? If I want to know dy dx here, you can see that, yeah. Dy dx we just got was minus x over y. Now we don't have to worry about signs here because we know that dy dx is this. If I choose this point here, 3, 4, the sign is already correct for me. I know that the slope of the tangent line is going to be minus 3/4. And had I went with this one down here, the slope of the tangent line will be positive 3/4 because the coordinates of this one, let me see. With this one down here, the coordinates of that are 3, minus 4. And if I plug that into dy dx, I automatically get the correct sign. So there is some utility to this. We're going to need to know how to differentiate things implicitly, because we're going to come to some of these equations where y is either very difficult to or impossible to isolate, but we still want to know what dy dx is. So this is about the easiest case I could think of, and I think it illustrates nicely that either way you do it, you get the same answer. So let's see, let's try something a little bit more difficult. We'll go with, try the same thing on this. Alright, okay. I want to know, what is dy dx? If we regard y as a function of x, what will dy dx be? So you do the same thing, d dx. Both sides, alright, the whole thing. So just differentiate each piece individually. The derivative of 3 of x cubed is, that'll be 3x squared, plus the derivative of this, once again, you have to do it, it's a chain rule problem. The outer function is the cubing function, and the inner function, as always, is y, the unspecified function y of x. So to take care of the outer function, it's going to be 3y squared. By the chain rule, that has to be multiplied by the derivative of the inside function, which we just symbolize as dy dx, or y prime. You could use y prime. I'm going to use dy dx just to emphasize the fact that y is a function of, that we're regarding y as a function of x. Equals, on the other side, just 2x, right? Because that's just x, plus this would be dy dx. Now, whenever you do this, you'll always be able to isolate dy dx. It's always going to work out where you can isolate dy dx. It might be tough and it might be messy, but it can always be done. And the way that you do it is, after differentiating, there will always be some terms that have a dy dx and some terms that don't. So what you got to do is take the dy dx terms and pull them on one side, take the non-dy dx terms, pull that on the other side, and look what happens. If I do that, I'll have 3y squared dy dx minus dy dx equals 2x minus 3x squared. After having done that, dy dx will always factor out of one of the factor out of the whole thing. So I'll take it out, dy dx. That should be a parenthesis there. So that was 3y squared minus 1 equals 2x minus, 2x minus 3x squared. And then divide through. So the last thing that we get on this, we finally get dy dx equals, I don't like negatives on my x squared, so I'm just going to flip that around, and I'll say minus the quantity, 3x squared minus 2x, divided by 3y squared minus 1. So we started out with this. After differentiating implicitly, we come up with the rate of change of y with respect to x is this expression. Now the question is, what does this mean exactly? For that matter, what does this mean? Well, all these things represent is just ordered pairs in the xy plane that satisfy this equation. It's the same deal as though we had said something like y equals, say, x squared. What does this actually mean? This is nothing more than the set of ordered pairs that make this equation true, right? Like 1 comma 1 makes it true, so it's on the curve. 2 comma 4 solves this equation, so it's on the curve. And we can't list them all, but we can graphically represent it with a parabola. So whenever we have some kind of an equation with x and y, it can always be represented graphically. So this is the graph of this. And in a similar fashion, the graph of this, the set of points that solve this equation, make a circle. And the set of points that solve this equation makes some other kind of graph in the xy plane. Now, we really don't need to know what these things look like, but they do make neat kind of patterns, so I printed up a couple. Let's see. This one in specific, it happens to be, I graphed it up with a program. That's this. Now you might think, how is this thing generated? How would we generate such a graph? without a computer, it would be really tough. But basically what you do is you plug in values of x and you get y values out, just like you would with a regular function if y had been isolated. For example, if in this equation, if we set x equal to 0, what we wind up with is the equation y cubed equal, right? If we let, I'm going to say, if we let x be 0, what we wind up with is y cubed equals y. And we can isolate, and so we get y cubed minus y is 0, and we can factor that and say y times y squared minus 1 equals 0, which gives us, so this means that if x is 0, y can be 0, positive, and negative 1. So if I make x 0, I get these 3 points here. I can plot these. And if I pick a different value of x, say I pick a value of x like 1/2, and I plug that in, I'll get a different equation with only y's in it, which in turn would have 3 solutions, right? 1, 2, 3 here. Now certain values of x you could plug in and only get one value of y out. If I plugged in, say, x equals 2, I would only get one solution for the corresponding equation because there's only one on the curve. But you just need to know what these things represent. They just represent, random curves in the xy plane. And I have a couple other ones that I thought were cool, just to show you how neat these things can actually be. This is a pretty popular one. Alright, this is called the folium of Descartes. We get x cubed plus y cubed is 3xy. Alright, if you plug in values of x, say, if I make, say, x equals 0, I wind up with the equation y equals 0, and I only get one single point. If I plug in x equals 1, I get 3 corresponding values of y. And if I plug in values of x over here, I'll only get 1 corresponding value of y. So that's a cool one. And another one I had was this monster here. And I don't know, you can see that, right? Let's see, it's got 2 branches. You don't really need to know what that is. It's just a really complicated expression. But look at it, 5th degree. So if I make x, say, equal to 1, what I'm going to have is a resulting equation in y, 5th degree equation, which is going to have 5 solutions potentially. And that's what happens here. If I make x, no, not 1. If I make x equal to like 0.8 or something here, what I get is I get 5 corresponding y values for that one x value. And that happens all throughout here. But this is the graph it makes. It's a curve that's implicitly defined, and just so we can put some kind of an image to what it is that we're actually doing here. And when we do things like find dy dx, we're finding expressions that gives us the slope of tangent lines to the function for various points. Like if we knew a point here was, say, I don't know, I'm just going to ballpark it at like maybe 1.8 comma 1.8, we could figure out what the slope of the tangent line is at that point. Alright, so let's see if we can make this a little bit harder, because they're not all so easy. Let me get my stuff out. Alright, so let's make this just a little bit more complicated to give us some practice with how to carry these operations out. I give you a curve implicitly defined as this, and I want dy dx. So just got to differentiate. So differentiate each term with respect to x. So this first one is going to be just 4x. 4x plus, and what do you do here? Well, you have x times y, and we're considering y as a function of x, so we need to do the product rule here. So I'll call this one f, and I'll call that one g, and I'll just work the product rule on it. So f prime is just 4, right? 4 times, so that's f prime g, so that's 4y squared, plus g prime f. Now g prime, we need the chain rule, so that's going to be 2y, right, dy dx. That's g prime f times 4x. Alright. Equals, and on the other side, the derivative of that we just symbolize as dy dx. If I want to clean this up, what am I going to do? I'll take this over to the other side, get all the dy dx terms on one side, all the non-dy dx terms on the other side, and that will leave me with 4x plus 4y squared equals dy dx. I'm just going to write it as y prime because we know what it means. Y prime minus, now if I take this to the other side and I combine it, that'll be 8xy y prime. Factor out the y prime, so you get y prime times 1 minus 8xy, and then divide through, and what you wind up with finally for this one is dy dx, or y prime, equals 4x plus 4y squared, all divided by 1 minus 8xy. I don't know what the curve looks like, and that's okay. It doesn't matter. All we need to do is practice how to do this, and we'll do applications later. So that's one way. A little more complicated would be something like this. Now this can be a bear, but it's really long, but it's still good to know how to do it. So we have y's and y squares. They're all caught up in trig functions, and we got chain rule and compositions and products and all that stuff, but we can still handle it. All you got to do is know chain rule. So differentiate with respect to x. We'll start on this side. The outer function is sine, so the first step to this side is going to be cosine. Let me come up here. Cosine of the whole thing, x plus 2y. By the chain rule, that has to be multiplied by the derivative of the inside as though the outside did not even exist. So a big parenthesis here. So that's going to be, the derivative of the inside is 1 plus 2y prime. All right, I don't have to do any chain rule here because it's just y prime sitting by itself. But that's how you get the right hand side. Equals, on the left we have to do product rule, right? That's f, that's g. So here we go. F prime g. F prime will be 2y y prime times cosine x, right? That's f prime g plus g prime f. Now since g prime is going to be minus sine, I'm going to say minus sine x times y squared. The y squared is on the outside, so I'm going to put parentheses around this just to be sure. Now you get this big long expression which barely even fits. I could write it that way maybe. But what we got to do is if I want to isolate y prime, you have to do a little bit of work here. You're going to have to multiply stuff out. I'm going to do it just to show you how, but in general I wouldn't require this on a test because it's just a bunch of algebra. But I said you'll always be able to isolate y prime, so I aim to show you that it is actually possible. We got a y prime floating in here and one y prime on the other side. But the bad news is the y prime is inside a set of parentheses here. So what we have to do, unfortunately, is distribute this to both terms on the inside. So that'll be cosine x plus 2y plus, now when this goes here, it'll be 2y prime cosine of x plus 2y equals the same thing on this side. Now, since I have one y prime term here, and I have a y prime term on the other side, sorry I have to keep moving this back and forth, I'm going to move this to the other side to group it with this one, and I'm going to move this non-y prime term to the other side and group it with this other one. So let me just clean that up. That'll be, let's see, 2y prime cosine x plus 2y minus 2y y prime cosine x equals, and when I move this over, that'll get a minus sign. That'll be minus, this term I'm going to rewrite because I want the y squared out front, minus y squared sine x minus cosine of x plus 2y. Alright, so you got this big mess. Alright, now it only looks bad, but if I can factor out a y prime here and divide through. So in total, I'm going to get, I'm not going to bother factoring out, I'm just going to write it. It'll be, at last, dy dx equals y squared sine x plus cosine of x plus 2y, all divided by, since both of the terms on the other side were negative, I'm going to just put the negative out front. That's how I like doing it. Divided by, now after factoring out a y prime from this side, that'll be 2 cosine of x plus 2y minus 2y cosine x. And that's the final result. That mess. So yeah, these things can get pretty crazy, but that's how it's done. As a final example, you do not have to have just x's and y's. You can have combinations like this. So we're going to, for purposes of doing this, we're going to suppose that there's some relationship out there, where u and v, that's a v, are both functions of another variable t. Let me zoom in on this, come in a little tighter. Alright, so we can see, we're going to say, for this problem, we're going to say let u and v be functions of another variable t. Now there doesn't have to be a t in here. Okay, we don't need to have these t's in order to be able to differentiate it with respect to t. But we're just going to assume that u and v are both based on t, and t is the variable. So we have two dependent variables, u and v, both functions of t. And I want to know what happens when you differentiate this with respect to t. So u and v are our functions. We could just treat those both as y, and t is our variable. So I'm going to do d dt to both sides of this. Now what's going to happen? The derivative of this with respect to t will be the derivative of the outside function is the squaring function, so that's going to be 2u du dt, right? Outside times inside, plus the derivative of this will be, since the outside function is the cubing function, it's going to be 9v squared by the chain rule dv dt, right? Plus the derivative of t squared, let me see, the derivative of t squared is just 2t, that's easy, plus, and for this we need the product rule, so f prime g, so that'll be t du dt, plus g prime f. Now the derivative with respect to t of t is just 1, so times u is just u, equals 0. I'm going to go a little wider here. Alright, can I see all that? Yeah, that's right, 2, yeah, alright, that's it. And the whole thing that you get is this. Now we will interpret what this means exactly later on, but it is a situation that we're going to encounter. We're going to have multiple functions of the same variable, and we're going to be answering questions about how do these two functions change as t changes. There's nothing really here to isolate. We could isolate du dt or we could isolate dv dt, but out of context, without any further context to what's going on in this problem, those things aren't really that important. I just wanted to do the video so you know how to treat this if it does come up. And as a final example, we don't have to use u's and v's exclusively. If I could say something like, I'll take this problem, I'll write it down again, so I'll say 2x squared plus, I'll leave out the 4 and just write xy, say, equals y cubed. What would we do if I give you this and I say, don't regard y as a function of x, but regard x as a function of y? So what's going to happen if x is, say, g of y, right? Y is the variable, x is the function. So what I want is dx dy in this case. I'm just making it up. We could find dy dx, or we could find dx dy. I just want you to get used to seeing, don't get used to seeing x exclusively as an independent variable and y exclusively as a dependent variable. They can be switched up. So last example, differentiate with respect to y, so x is the function. Alright, so when I differentiate this with respect to y, it's going to be 4x, because that's the outside function, times dx dy, plus, got to do product rule here, so f prime g, that'll be y dx dy, right, because it's f prime is dx dy, g is this, plus g prime f. Now g prime is just 1 because y is considered the variable, times f equals, and since y is a variable here, that'll just be 3y squared. And we could isolate it if we want, but I'm not in that kind of mood. And that's it. That's like a first lesson crash course in implicit differentiation.